The Euclid Space Telescope just sent back its first images, and scientists weren't ready for what they found. This isn't a telescope built to zoom in on one galaxy. Euclid was designed for something far larger and far more unsettling. Its first image mosaic covered 260 frames, spanning an area 500 times larger than the full moon. And inside that data, in a galaxy first observed in 1884, was a secret that 141 years of astronomy had completely missed. This is what they saw, and this is why some of them are calling it terrifying, once you understand what you're actually looking at. The thing they weren't ready for. By March 2025, the results from the first real week of scanning were sitting on a screen. Scientists looked at what Euclid had returned. Then they reached for a word they'd spent entire careers avoiding: crisis. Not because the telescope broke, because the universe showing up in the data didn't match the universe the math predicted. Galaxies had appeared too early, arranged too fast, built themselves into massive structures before the equations said they should have been able to. And inside a galaxy cluster that astronomers had spent decades studying, one they considered completely understood, Euclid found 630 objects that every prior instrument on Earth had missed completely. But that isn't the picture that scared scientists. The one that did was found before the science mission even started, in a blurry test frame, inside a galaxy we've been photographing since 1884. What was hiding in it changes everything you're about to hear. But here's what you need to understand before any of this makes sense. Imagine everything you can see right now. Your hands, the ceiling above you, the buildings outside, the entire planet you're standing on, every star visible on a clear night, every galaxy ever captured in a photograph. All of it together adds up to 5% of what's actually in the universe. The other 95% is invisible, not distant, not hard to see, invisible. It doesn't give off light, doesn't reflect it, and no instrument humans have built can detect it directly, but it's there. We know it's there because of what it does to the things we can see. We call the first part dark matter. Galaxies spin. They spin so fast that if only the visible matter inside them were holding them together, they'd fly apart like mud off a spinning wheel. Something invisible is holding them, and it makes up about 27% of the universe. We call the second part dark energy. The universe is expanding, and not just drifting outward at a steady pace. It's accelerating, getting faster every second, like something is actively pushing everything apart. We don't know what's going on. We call it dark energy, and it makes up about 68% of everything. 27 plus 68 equals 95. 5% for everything you've ever seen or touched or studied. The rest is a mystery. So, we built a €2 billion telescope called Euclid to find answers to what we do not know. Euclid finds dark matter by watching how invisible things bend light. Imagine a candle across a room. Now, someone holds a glass ball in front of it. The light bends around the glass and warps into a ring. The ball is the lens. Euclid does the same thing at a cosmic scale. When an enormous concentration of dark matter sits between us and a distant galaxy, its gravity bends that galaxy's light. The image stretches and warps. By measuring exactly how those images distort across hundreds of millions of galaxies at once, scientists can map where the dark matter is sitting, like seeing the glass ball by watching what it does to the light behind it. Euclid carries two instruments for this: a visible light camera that covers an area of sky equal to 2 full moons in a single shot, with enough sharpness to pick out individual galaxies inside all of that, and a near-infrared detector that measures the distances and masses of billions of galaxies at once, placing each one precisely in 3-dimensional space. No telescope before it could do both. Either you got the wide view or you got the detail. Euclid gets both. Routine science observations started on February 14th, 2024. In 1 week of scanning, it returned 26 million galaxies. The farthest one is 10.5 billion light years away, meaning its light left before our solar system existed. And what it found in that 1 week is the part nobody planned for. The standard model of the universe might be broken, not due for a small update, not reaching the edge of its usefulness, broken in a way that can't be quietly explained away anymore. Here's the problem. Scientists have 2 separate ways of measuring how fast the universe is expanding. Think of them as 2 independent clocks, both trying to measure the same thing. The first clock looks backward in time. It uses the faint glow of ancient light left over from just after the Big Bang, measured with extraordinary precision by a satellite called Planck. From that ancient signal, scientists calculate how fast everything was moving at the very beginning and what the expansion rate should be today. The second clock looks at what's happening right now. It tracks nearby galaxies moving away from us, using a special type of star, and a special type of explosion as measuring tools. Both have been tested and refined for decades by independent teams around the world. Two clocks, same universe, different answers. The gap between them is what scientists call the Hubble tension. At a conference held specifically to examine this problem in Corfu, Greece in September 2025, researchers confirmed the gap had grown past 5 sigma. That means the probability this is just a statistical fluke is less than 1 in 3 million. Physicists are not a profession that reaches for dramatic language easily. They will argue for decades about whether to use the word significant before committing it to print. At that conference, they skipped straight past it. They used crisis. Euclid was built partly to settle this. Its first major cosmology data release is October 2026. That release will be precise enough to say which expansion rate measurement is right, or to confirm something much more uncomfortable, that both measurements are right, that they're both accurate, and that the model itself is missing something we haven't discovered yet. Alongside the Hubble tension, there's a second problem called the S8 tension. This one measures how clumpy matter is across the universe. The model predicts a specific number. Surveys keep returning a lower one. The universe looks slightly smoother than the equations say it should be, not dramatically different. But in cosmology, 1% off in the right place isn't a rounding error. It's a signal that something in the foundation is wrong. Euclid's weak lensing data is supposed to settle this question too. The results are still coming in. Cosmologists built a framework called lambda cold dark matter over decades. Lambda for the cosmological constant, a term Einstein added to his equations to explain a static universe, then removed when Hubble showed the universe was expanding, which now describes the dark energy pushing that expansion to accelerate. Cold dark matter for the invisible substance whose gravity built everything. This framework underlies every prediction ever made about how galaxies form, how the universe grew, and where everything is headed. The tensions Euclid is testing aren't a footnote to that framework. They're a question about whether the ground it's built on is solid. If October 2026 confirms what the early scans are suggesting, every astrophysics textbook currently in print needs its core chapter rewritten. But even a broken standard model isn't the most disturbing thing Euclid has found. What 1 week found. On March 19, 2025, the European Space Agency released Euclid's first batch of real survey data. 1 week of scanning across 3 patches of sky, 26 million galaxies. 380,000 of those were individually sorted by shape and structure, forming the first galaxy catalog ever built entirely from Euclid data. Scientists compared the variety of galaxy shapes to a question Charles Darwin had about flowers, calling it an abominable mystery, meaning, why has nature produced so many different forms? Galaxies can be flat spirals, round blobs, chaotic tangles, or perfect rings, and nobody fully understands why. With 380,000 examples from a single week, Euclid handed researchers the biggest data set ever assembled to begin working it out. That's the headline, but here's what's hidden. Inside those 380,000 classified galaxies, scientists found 500 gravitational lens candidates. These are places where a galaxy and its invisible dark matter halo are bending the light of another galaxy sitting directly behind it. The same glass ball effect described earlier, except happening naturally across the cosmos. Almost every one of those 500 candidates had never been identified before. Before Euclid launched, the entire history of human astronomy had produced fewer than 1,000 known and well-imaged gravitational lenses. Total. Every observatory, every space telescope, every survey ever runs. 1,000 accumulated over a century of looking. 1 week of Euclid scanning found 500 new ones, at 14% of its planned survey area. By mission end, Euclid expects to find 100,000. Think about what that gap means, not just for science, for what it says about how much we were missing. 100,000 locations where dark matter is dense enough to visibly warp the light of an entire galaxy sitting behind it. All of them were always there, bending light, shaping space. We just didn't have the right tool to see them. The Euclid Deep Field South, in one of the 3 regions in the March release, had never been examined by any prior deep sky survey at all. One pass. Euclid found more than 11 million galaxies in a corner of the sky nobody had properly looked at before. You'd expect the surprises to live in unexplored places like that. New things and new territory. That's the comfortable story. But then there's the Perseus cluster. Perseus is 240 million light years away, one of the most studied galaxy clusters in the sky. Astronomers have spent decades on it, published papers, named galaxies, mapped distributions, cataloged structure. They built a detailed, peer-reviewed working model of the cluster. Euclid looked at it and politely disagreed. Inside the Perseus cluster, Euclid found 630 dwarf galaxies that every prior instrument had missed completely. 630 objects sitting inside a region considered fully understood, invisible to everything that had ever pointed at it. Dwarf galaxies are very sensitive to dark matter. Their shapes and positions work like tracers, pointing to where dark matter concentrates. Finding 630 new ones in a cluster we thought we'd fully mapped doesn't just update the dark matter picture for that region, it replaces it. If we were that wrong about Perseus, a place we'd spent decades studying, what are we missing in places we've barely glanced at? Here's the part that reframes all of it. The architecture nobody built. Galaxies are not the architects of cosmic structure. They're the decoration. This is what Euclid's data makes impossible to brush aside. Dark matter doesn't float around the universe evenly. It collapses. It pulls itself into massive invisible clumps, some larger than entire galaxy clusters, under the force of its own gravity. Scientists call these dark matter halos. They form first, long before any stars ignite in any galaxy. Those halos are already there, already shaped, already determining what the universe will look like. Galaxies form inside them later, lighting up regions that invisible matter had already organized. The light comes second. The structure was always underneath. Every image of space you've ever seen, every Hubble photograph pinned to a classroom wall, every galaxy picture ever printed in a science magazine is a photograph of something that formed inside a dark matter halo. It didn't build. We've been taking pictures of the decoration and calling it the universe. Euclid can map galaxy shapes and gravitational lensing distortions simultaneously across millions of objects, showing this hierarchy in a way no prior instrument could manage. The cosmic web, enormous threads of dark matter stretching hundreds of millions of light years, doesn't just organize galaxy clusters at the largest scale. The same invisible forces shaping the biggest structures in the universe also determine how stars form inside small, irregular galaxies. Large scale dictates small scale. An invisible thread, hundreds of millions of light years long, quietly controls what happens inside a single galaxy's star-forming region. The universe doesn't work in separate layers from big to small. It's all connected at every scale. The visible universe is riding a framework it didn't build. Euclid's November 2025 data release added one more piece. A paper by Fabrizio Gentile and the Euclid collaboration analyzed thousands of galaxies in different environments. In dense regions where galaxies cluster together, they found galaxies losing their ability to form new stars before their central structures had even developed. Star formation stops before the core forms. The model predicted the opposite sequence: core first, then star formation shuts down. Euclid found the reverse in thousands of galaxies at once. The invisible framework isn't just deciding where galaxies form, it's deciding what they become before they finish forming. If dark matter built the environment that visible matter moved into, then everything we've ever observed through a telescope is downstream of something we can't see. A map of the afterthought, not the architecture. And while Euclid was busy showing us all of this, before its main results were even published, it found something that had been hiding in plain sight for 141 years. The Ring. September 2023. The science mission hasn't started yet. Engineers are running calibration tests, taking deliberately blurry images just to check the optics before real observations begin. These are throwaway frames. Nobody expects to find anything. That's the whole point of test data. Bruno Altieri, Euclid's archive scientist, goes through the frames looking for instrument problems. He found something else. He flags it. Euclid takes a second, focused pass at that patch of sky, and the blur resolves. A perfect ring of light surrounds the center of NG, C6505, an elliptical galaxy 590 million light-years from Earth. Lewis Swift first observed NGC 6505 in 1884. It went into the catalog as a bright yellowish blob, unremarkable. For 141 years, every telescope with enough resolution to examine it has examined it. The Hubble Space Telescope, ground observatories on multiple continents. Not one of them found anything unusual. The ring was never detected. What Altieri found is called an Einstein ring. When a background galaxy, a foreground galaxy, and the observer line up precisely enough. The background galaxy's light bends completely around the foreground galaxy and forms a perfect circle. Einstein's general theory of relativity predicted this could happen. It does happen. It's extraordinarily rare. Less than 1% of all known galaxies show this effect. Before Euclid, fewer than 1,000 had been well imaged in all of astronomy's history. Euclid found this one in calibration data. In a galaxy classified in the 19th century, before its science mission had technically begun, Connor O'Riordan of the Max Planck Institute for Astrophysics led the paper analyzing the ring. He said, "All strong lenses are special because they're so rare. This one is particularly special because it's so close to Earth, and the alignment makes it very beautiful." Matt Page of University College London, who leads Euclid's visible light camera team, said, "Astronomers have been imaging this galaxy for more than 100 years. But it took the super high resolution of Euclid to reveal this amazing Einstein ring. 141 years. Every major telescope. The ring was there the whole time. That was before the real work started." What has no name. The ring around NG C6505 isn't being made by NG C6505 alone. An Einstein ring needs a background galaxy. Something sitting behind the foreground galaxy, aligned precisely enough for its light to wrap around it. The ring you see in Euclid's image is the background galaxy's light. NG C6505 is just the lens. Something behind it is the source. That source galaxy is 4.42 billion light-years away. Its light has been traveling toward us since before complex life existed on Earth, since before the continents we live on took their current shapes. For billions of years, it has been sitting directly behind NG C6505, bending space around it, quietly warping every image ever taken of that galaxy. It has no name, no catalog entry, no record in any astronomical database. It doesn't officially exist. Valeria Pettorino, the European Space Agency's Euclid project scientist, said this when the ring was announced. This ring was observed within a well-known galaxy, which was first discovered in 1884. The galaxy has been known to astronomers for a very long time, and yet this ring was never observed before. This demonstrates how powerful Euclid is, finding new things even in places we thought we knew well. Finding new things in places we thought we knew well. The terrifying part of what Euclid is showing us isn't explosions or disasters. It's something quieter and harder to shake. It's the realization that the things we thought we'd already finished understanding were never finished at all. The Hubble tension tells us the universe's expansion rate doesn't match the model we've trusted for decades. The Perseus cluster was hiding 630 objects inside a region every prior survey called complete. 500 previously unknown gravitational lenses turned up in 1 week of scanning 14% of the sky. And NG C6505, a galaxy we've photographed since 1884, was hiding a galaxy 4.42 billion light-years behind it that has never been named. All of that from 14% of Euclid's planned survey, and from test data taken before the real mission started. The first primary cosmology data release is October 2026. That's when Euclid's measurements will be precise enough to test the standard model directly, to say whether the expansion rate matches the equations, to say whether the Hubble tension means we need new physics or just a corrected measurement. The answers will not be small either way. 86% of the survey area is still blank. Euclid is expected to image roughly 1.5 billion galaxies by the time its primary mission ends. It will find 100,000 gravitational lenses. Each of those is a dark matter concentration that's been silently bending light around it for billions of years. Unnamed, unmapped. Each of those 1.5 billion galaxies is a potential N, GC6505, hiding something behind it that nobody has ever seen. The unnamed background galaxy has been 4.42 billion light-years away for 4 billion years. During every observation Lewis Swift ever made of NG C6505 in 1884, during every photograph taken since, during every analysis ever published, that galaxy was in the same position, behind it, bending its light, distorting every image. It took a blurry test frame from a telescope we launched in 2023 to finally see it. It has no name, no catalog entry, and it's been there the whole time. The real question isn't what Euclid found in the 14%, but what we do with the answer once it comes. If, in October 2026, we learn the model is broken, it means everything we thought we knew about the universe was based on something incomplete. Some scientists might see that as progress, while others could see it as the most unsettling discovery in astronomy's history. Whether you find this exciting or frightening depends on how you feel about learning that the universe you thought you knew was never quite real.